Okay, let's keep adding to our vocabulary and what we know about these. So in mathematics, a model is an equation, a table, or a graph that's used to describe reality. So we're using something to model this so we can make sense of it, right? The red curve in figure 3, so you can see it, it's this red part that goes right through there, is a model called a normal curve, all right? So a normal curve is that bell-shaped curve, which is used to describe continuous random variables that are said to be normally distributed. Now, here's the deal. We had the uniform is what we talked about over here, where it's just this box. Well, that doesn't happen very often, right? That's not the common way that this plays out. So what we're typically looking at with data, it doesn't always just everything is equally likely. That doesn't happen. So we're looking here, and this red curve, notice all my values here are the same as this red curve, as this red curve. All of those red curves are exactly the same. Now the question here, because it's figure 3 and it's this red curve in figure 3, so all 3 of those are the same. The deal with this is, look at this first one, right? So they're all here with the 100 in the middle. There are 1, 2, 3, 4, 5 rectangles in the first one. Look at these gaps. This is up above, gaps, gaps. There's issues happening there, right? Well, look at this one. Smaller gaps that I'm looking at. And then look at this one even still. Almost nothing, right? So what is the difference between A, B, and C? More rectangles, right? We're making our intervals smaller here so that whenever we're filling it in more, when you have great big intervals on these rectangles, then it's not as accurate. The more rectangles you can put in here to fill in that curve, the closer you get to the shape of the curve. I'm going to write that down. The more rectangles, the closer to the shape of the curve, right? So I just want to make sure you see that. The normal curve, nonetheless, right, is this bell curve that we're looking at here. And that's making that the normal look. Normally distributed, all evened out across the way. All right. So a continuous random variable is normally distributed or has a normal probability distribution, liking those words, aren't we? If its relative frequency histogram, relative frequency histogram has the shape of a normal curve. Normal curve. I ran out of room because I write big. So here, a continuous random variable is normally distributed if it has the shape of a normal curve. So the more rectangles I put in there, if my shape of those rectangles, if it looks like, if I go around them and it looks like a normal curve, that's a normal probability distribution and it's considered normally distributed. All right? Okay. So kind of what we've already been talking about. We're continuing and we're just going to make it more of a probability model and really talk it out about what that looks like. All right. So look at this. Properties of a normal density curve. So we've got a couple of graphics here because I want you to see the difference in what's changing with the mean and the standard deviation and how that looks. All right, so here's some properties. Let's go through those. A normal curve is symmetric about the mean. All right, so this normal curve is symmetric about the mean. Whether it's over here or whether it's over here, it still looks like a normal curve, right? Like what we were seeing up above. Because the mean, the median, and the mode, they all equal each other, the normal curve has a single peak and the highest occurs at the mean. So it's a single peak at the mean. That's the key there. Okay? A normal curve has inflection points at 1 standard deviation. So an inflection point, that's just a mathy term. So that means I'm changing concavity. So this is concave up, and it's going to go to concave down. So concave down means it goes like this. Concave up looks like the bowl is up. Concave down, the bowl is down. And it changes concavity at the first inflection point. All right, that's what this is saying. The area under the curve is 1 because it's probability. Area, probability, these are words that are meaning the same thing for us. The area under the normal curve to the right of the mean equals the area to the left, which is half. So that means when you have this set up, I'm just going to make a random little deal up here. So first of all, it's right here at the mean. That splits it up. Half is to the left. Oops. So this is half, and then half is to the right of the mean. Each one of those are half of the area, right? No duh. That's what this is saying. So the area under the curve is totally 1. To the right is half, to the left is half, because the mean is what splits it, because that's what everything is telling us all the way up to this point, right? As x increases without bound, means gets bigger and bigger, the graph approaches but never reaches the axis. As x decreases without bound, it approaches but never reaches the axis, which means, look at how close this is. So if I were to zoom in as close as possible, they're saying this gets so close but never actually reaches it. It just rides it. So close but never actually reaches it, just rides it. So it cannot go below this axis. That's not acceptable. Cannot be up here way high. That's not acceptable. It gets as close as possible to that axis. That's what it's talking about. All right? Okay. Now, I also want to show you this. So check this out. If you change the mean, so the mean is the center of the bell curve. That's my mean, right down the center that I'm looking at. So look at what's happening in this part A. My mean changes, but this goes from 1. My mean here is a 3, but my standard deviation is a 1 to 1. My mean is a 0, but the standard deviation is a 1. Do you see how that's coming? And my standard deviation stays the same. Because the mean is the middle of my curve, when that changes, it shifts the whole thing. So the standard deviation tells you how far apart this is. We'll talk about that here in a second. But the mean, when the mean changes, then that means my whole entire graph shifts. Shifts the graph. That's what that's telling us. Okay, now look over here. When my mean, that's a mu, stays the same, but my standard deviation changes, all right, look at what's happening here. My mean is at 0, so that means my peak is at 0 no matter what. So right here, whether it's the blue peak or the pink one, this graph still centered at my mean. The difference here is for this pink one, I have a standard deviation of 1 to hit that first inflection point. It only goes over 1. For the blue, I have a standard deviation here of 2. Pardon me. So it goes over 2 before I hit my first standard deviation. Do you see that? So what's happening? The smaller the number, it's a tighter graph, right? So it's closer to the mean, because standard deviation just means distance from the mean. We've already talked about this. So the bigger the standard deviation, the more spread out the data. Haven't we talked about this already? And we're bringing that into the current lesson. The more spread out, the bigger the mean, the farther away that is. The bigger the standard deviation, the farther away it is from the mean, and the more spread out is the data. Cool, right? So when the mean changes, you shift the entire graph. When the standard deviation changes, this makes the graph either more narrow or spread out. That's what it's saying. Wow, look at how weird that looked. That D got a little crazy. More spread out. All right? Okay, let's look and see what this is saying here to finish this off here real quick. Properties of the normal density curve. So the empirical rule, which we have all seen before, right? This is just the exact same graphic that we've seen before. This is not brand new information that we're looking at, but this is normally distributed. This is just the empirical rule. You've got your mean and your standard deviations. 68% is 1, 2 standard deviations, 95, 3 standard deviations. So that's part of the properties. All those other properties we just talked about and the empirical rule holds true. Nice, right? I love it when we can have previous information into the current lesson, and that's what we're going to keep doing. So knowing what we did previously, it's all going to start coming together and we can see how it all relates.